I see Will shaking his head. How many of you have programmed in OpenGL before WebGL? A quick show of hands. Oh, okay, all right. It seems like Will and two other people are the only ones. How many people found the shading language ELSL intuitive to use with JavaScript? There's not much to compare with. All right, that's probably tough to judge. My impression is that the shading language is the least of our worries with that. It's just a more question of functionality and getting it to work. All right, anyway, thanks everyone, and today I will be talking about surfaces in general, mostly isosurfaces. The last slide this lecture that we had back in, I guess, early November, I talked about basically three very in-depth topics and crammed them into one lecture. So I talked about basics of 3D graphics. Things you should remember from that are rasterization versus ray tracing, how the fixed function rendering pipeline, mostly for rasterization, works, and where both indirect and direct visualization techniques fall into that. You should remember volume rendering, and especially the idea that volume rendering as we conventionally do it is an emission absorption model. You should remember classification, the idea that we're applying a transfer function to samples that are being interpolated in space, and the blending operation. These are all things we covered last time. And for transfer functions, you should be able to talk about the difference between 1D and 2D transfer functions. And on that note, I will go back to slide 117, where I was trying to wrap up 2D transfer functions rather speedily last time. Before I do that, I'm just going to go through a quick recap of volume rendering. These are probably the most important formula and general concepts to remember from volume rendering. The key thing is that it's an emission absorption model, and emission refers to the color. Absorption refers to the alpha, which is a scalar value. There is, derived from the Kajiya rendering equation, there is a continuous volume rendering equation that for some reason everybody attributes to Sabella's 1988 paper, although I never saw anything like that in that paper. So probably the most common way to dig up this integral is to refer to the NIST paper from 2003, and there are several others that have something more or less in this form. But the basic idea here is that you have two nasty nested integrals, and you want to find a way of turning that into a discrete summation of some kind. And that's exactly what we did in the last lecture. We converted that into a discrete Riemann sum, the sum of a product of essentially alpha blending operations. And the way we implement this in a shader, or really any place where we're doing front-to-back compositing, is using this front-to-back blending operation, where we're taking the next color is the previous, so this would be the back sample as the front sample, plus 1 minus alpha color, and same thing for alpha. And we just chain these over and over again, and since everyone did homework 6, this should be pretty familiar by now. Now I'm going to go back quickly to the last slides from, there we go, all right, from the transfer function lecture. And we're going to talk about why to use 2D transfer functions. Well, the idea here is if you have a 1D transfer function and you're looking at something like bone in the tooth, it's fairly easy to look at just that and plot down an iso value. And if you're not exactly sure where it is, you can make a 10 function that is increasingly thin as you get close to the isosurface, or thick if you want to have some sense of where the gradient, if you want it to be more or less fuzzy. And if you increase the opacity or decrease the opacity, then this will make it more or less opaque or transparent. However, in some cases, one isosurface is not going to be enough. And what Jonas and others, going back to the, I guess, late 90s, early 2000s, realized, David Laidlaw Brown also had a heavy role to play in a lot of this research, was that you could actually look at a transfer function as a function of two values, not only value itself from the scalar field, but gradient magnitude, specifically inverse gradient magnitude of the scalar field. And by classifying both of these, you could actually start to get better classification of mostly medical data sets. And what we're trying to do here is we're trying to pull out regions where there are mostly noise, where there are interfaces between tooth and dentine, and we're trying to be able to classify really material boundaries. That's what 2D transfer functions, what classifying the gradient really lets us do. And the idea is that you don't want to just classify the gradient. That's not enough in itself. You really want to classify both the gradient and the original scalar field value. And by doing so, you will have a way of being able to identify these two materials. So that's exactly what we're doing here. Here we're actually taking away some of the, let's see, we are taking away the, let's see, the blue should go away. Yeah, okay, oh yeah, I see. We're just lowering the opacity contribution of the blue feature, which is the dentine, and you end up with something like this. So you're able to achieve very nice classifications in 2D compared to what you'd be able to do with 1D. And you're even able to classify things like curvature and apply this to 3D transfer functions. This is, again, more along the lines of David Laidlaw's research, and Gordon Kindleman later investigated a lot of these concepts. And I guess if you wanted to see it in one picture, not for this small tooth data set, but for a more complicated medical data set, this is what you'd see. The original 1D transfer function, you're going to get kind of fuzzy, noisy boundaries out of it. And with gradient magnitude classification, you're able to more accurately highlight gradient and classify the material boundaries that you want to see. So the advantages of multidimensional transfer functions, and again, I'm only talking about 2D transfer functions from 1D scalar fields, so from univariate data. The advantages are that you have this control over how to classify the gradient, and you get much higher quality visualizations with a lower sampling rate. So a lot of the magic that you'd have to do for production viz, I think there was this image from Lisa Avila several slides ago, where this was lovingly, this image, where this was lovingly classified from a 1D transfer function, but it took hours to figure out what a good 1D transfer function was, and then you had to use a very, very high sampling rate to actually reconstruct that. So this rendering took a very long time. And with a 2D transfer function, very often you're able to get something like that interactively. So the disadvantage is that you need some sort of user interface to control two dimensions instead of just one. And understanding the relationship between gradient magnitude and where the boundaries are can be non-intuitive at first. Most people, unless you use tools like SkiRun and ImageViz 3D and I guess now Visit to some extent, but unless you use these on a regular basis, I would say that the number of people who really use 2D transfer functions on a daily basis is still relatively low. Everyone knows they have potential, but even now, over a decade since they were first introduced, I would say they're still fairly an ideal, more of an ideal than common practice in visualization. So how would you actually manipulate 2D transfer functions with a widget editor? Well, this was a paper that Joe Niss had, and starting in Viz 01, and they ended up having a very nice IEEE Viz paper in 2002, I believe, on this as well. The idea here is that you want to pick things in 3 space directly using this little pointer widget, and then that's actually going to pick the color that you want, and it's going to try to match it with these arcs in the joint histogram. The joint histogram plots essentially value on the x-axis, and then inverse gradient magnitude on the y-axis. And using these arcs, you're going to be able to find out where the gradients are, and you're going to be able to plot features in the gradients with the help of this picker tool. So it's very much like what you'd see in a 2D 2D image processing application, a little bit like the magic lasso or color picker, except that instead of picking color and then applying a single color, it's picking color and applying a whole mapping from the 2D transfer function. So this is probably the best interface that we currently have for 2D transfer function visualization. And this is in SkiRun, ImageVis 3D. Yeah?
How does the 3D pointing work?
Huh?
How does the 3D pointing work?
I've only seen it in use once. I'll see if I can dig up the video and post that to Piazza. My understanding is that you basically drive it with your mouse and you pick a color, and so it's sort of a little bit like brushing and linking, except it would actually link to these sort of widget lines in the interface. So this white line right here, and that's sort of being driven by this opaque region of the transfer function editor. But I think other than that, it's just you're clicking with the mouse, you're determining the opaque regions you want to guide the rest of the transfer function, and then it will sort of fill in the rest. It probably would make more sense with the video, actually. That's a good point.
Seems like it'd be easier to drive an interface to control a 2D transfer function if you could somehow like move the interface too, like you had in your slide. You could have that little plane is rotating around. That seems like more.
So there are lots of different interface controls here. One thing I do remember is that all of these 2D widgets that are representing sort of the width of the triangles, these are in a sense looking at bits of your distribution, bits of your two-dimensional distribution in range space. This is really range space that you're looking at, two-dimensional joint histogram range space, but if you really wanted to get technical, this is really the read space. And the idea is that you'd actually be able to control the width of these widgets, and these widgets in the end are sort of the gradient highlighting tools that are giving you colors in your transfer function. And the idea is that you want them to be triangular because as you get close to 0 inverse gradient magnitude values, you don't really want to have to divide by 0 in the gradient domain, so that's something you really want to have close to 0 anyway. But as you get closer to the positive axis, as you go up the positive axis in the gradient magnitude space, you want to be able to spread out your classification. So that's, and it's interesting, I mean, a lot of these same concepts generalize to an isosurfacing technique, or an extension of isosurfacing called fiber surfaces, but that's more recent research. I can talk about that offline for anybody who's interested. But moving on, so that's 2D value and gradient magnitude transfer function classification. There is, in addition, there are even more sophisticated ways of doing multidimensional classification of univariate data. And one of these is using curvature. Gordon Kindelman used this to essentially look at, so he was also using this for medical data sets, a lot like these right here. But he realized that you could actually use curvature to better classify the boundaries, although there's not nearly as intuitive an interface for that. You're all of a sudden stuck with something a lot more like this, where you're able to plot regions in space that all of a sudden correspond to gradient magnitude and curvature, but you're not really able to do much beyond that. So in a sense, this was a very interesting paper, but classifying curvature is still much more of an experimental technique. It's more of a proof of concept that you can do it, as opposed to proof of usable user interface for controlling gradient magnitude, value, and curvature. Lastly, so what I've talked about so far are multidimensional classification of univariate data, mostly medical data from CT scan or MRI, well, I guess really CT scan mostly. And what we're going to talk about here are multidimensional classifications of multivariate data. So all of a sudden, your volume data have not just one attribute that came with the simulation or scan, but multiple attributes, like maybe a pressure or density or temperature. This is a much more difficult problem. And one of the simplest ways you can do it is, instead of using these piecewise continuous transfer functions from a 1D texture or a 2D texture in the case of gradient magnitude classification, you can actually approximate them as blobbies, as Gaussian blobs in all dimensions. And in theory, you have unlimited numbers of dimensions that you can create your blobs in, and then create a transfer function in n-dimensional space out of that. What's nice about this paper is, and something like this technique, not exactly this technique with Gaussians, but concepts like this date back to the work of Laidlaw in the late 90s. What's nice about Jonas's work in 2003 was that he found that you could analytically integrate between samples by integrating integrating in transfer function space itself. And that analytical integration turns into a bunch of error function terms, which are not exactly numerically integrable, but you can approximate them very efficiently. And you're able to essentially render something very close to the analytical ground truth, like the image on the left, instead of the image on the right, which would take a lot of samples the old-fashioned way, or the image on the far right, which is the same number of samples as the image on the far left. So in short, there are techniques for this. Again, finding user interfaces to govern multi-field, multi-dimensional transfer functions is a big challenge and not something that they covered in the paper. In terms of user interface design for multi-dimensional classification, there is a lot of recent research on this topic, and there are no silver bullets. But I can say that there are several papers that at least seem to me an interesting step in the right direction. One was a paper from Pacific Viz 2011, which was using parallel coordinates to give an overview of the multi-dimensional range space, and then draw these, essentially draw lines in the parallel coordinate space, I guess really regions in the parallel coordinate space that would correspond to color regions in domain space. And there's this more recent work by Xusen Liu and Bei Wang, and this is also ongoing, that's using dynamic projections for, and trying to classify scatter plots that are projected dynamically according to more sophisticated data-driven clustering methods, and volume render data sets in the same fashion. So the nice thing about these techniques is that they're actually solving a pretty challenging problem, and they're paying some attention to user interface design. The disadvantage is that it's really tough to figure out what exactly you're classifying and clustering. It's non-intuitive in some ways, and in the end, when you end up volume rendering something like this, you end up with not so much clean, crisp surfaces that you can understand, but big, general, colorful blobs that tell you maybe some correlation between variables, but not much more than that. So that's, I think, an ongoing challenge in multi-field volume rendering. Let's see, now we will go back to the surfaces topics. And before I go on to surfaces, I will mention one last volume rendering transfer function paper that I think, if you go into this field, will come up over and over again. And this is the Preintegrated volume rendering paper from Klaus Engel and Martin Kress and Tom Ertl in 2001. And the idea of this paper is that instead of just sampling discretely in samples in space and picking one sample in transfer function space, you actually can integrate along a block of samples in transfer function space, along the range space of the transfer function. And you can pre-integrate or pre-store that integrated color and opacity table into a 2D lookup table that you can then essentially query in between pairs of samples, in between a front and a back sample. And what this lets you do is it lets you achieve much, much higher quality with fewer samples, because you're sampling more accurately in the range space, in the transfer function domain, than you would otherwise. And so I'll just throw this up really quickly. But if people wonder why one person's volume renderer is slow and looks horrible, whereas another person's volume renderer looks great, very often it's a trick like pre-integration that is making one volume renderer much more effective, or much higher quality than another for the same number of samples. So today, we're going to be talking about surfaces. And surfaces are mostly a way of doing indirect visualization of 3D scalar fields of volume data, but not always. Before I talk about what an isosurface is, or contours, or go into terrain rendering, I should probably talk about implicit versus explicit. These are heavily overloaded terms in graphics. And in fact, in a sense, you can say implicit and explicit geometry and topology, similar to what we had with structured and unstructured data. They're not exactly the same concept, but they have some relation to each other. Generally, implicit versus explicit refer to how we reconstruct a geometry from a scalar field, or from something that is not explicit geometry. So explicit geometry is defined by vertices. And the best example I can think of that is a triangle mesh, where you have vertices and indices explicitly enumerated. And then you just need to send it to the rasterizer and render it. Implicit geometry is defined in 3D by an ISO value of an implicit function. And when we say implicit function, that's usually something like f of xyz equals value. And the f of xyz is called the kernel of the implicit function. And this may sound like a confusing bit of terminology, but this implicit function, for all intents and purposes, is the scalar field. It is the volume data set that we're talking about. So when we say an implicit surface, we're talking about an isosurface of volume data. And lastly, to confuse everyone just a little bit more, I'll mention parametric geometry. Parametrics are, in a sense, neither explicit nor implicit. They can be either or both. Depending on the parameterization, you can have a parametric form that converts to a scalar into explicit triangles via just an expression, and you can convert this into an implicit in some cases, and in other cases you actually can't. You have to explicitly subdivide it into geometry. If you're interested in that, I recommend taking Lane Cohen's CAGD class. In practice, in visualization, we don't end up with too many parametrics, at least not data that is in parametric form that we want to visualize. This is not always true. There's certainly high-order finite elements that use parametric forms, but most of the time, we don't use parametrics as a raw surface rendering modality. So in the end, we don't need to worry about that too much. And as I mentioned before, indirect visualization, as we're going to be talking about in this lecture, generally involves turning implicit geometry, or a scalar field with an ISO value that's defined, into explicit geometry that we're then going to rasterize. So here's some simple examples that I pulled from Hao Li's slides. He's a professor at USC. And in fact, this is maybe a little bit deceptive because the explicit form here is actually a parametric form. We just happen to have a closed form representation for it instead of explicit vertices. But this is the explicit form of how you define a circle in two-space. And the implicit form, this f of xy as the square root of x squared plus y squared minus r, that's the implicit form of the circle. And you can see you have the interior of the circle. This is, on a slide I'll talk about in a little bit, this is the sublevel set. Then you have the outside of the circle, this is the superlevel set. And the isosurface, the level set at R, is this black line. And this concept applies not just to analytical algebraic surfaces and curves and analytical expressions, but to data that are in raster form or in vector form. And generally the idea is that if it's in vector form, if you have vector graphics with points and vertices, this is an explicit representation. And if you have a scalar field, so raster data, and it's more like an image, then this would be an implicit representation. Both of them are piecewise approximations, just in different ways. The way we represent explicits in 3D are triangle meshes, points, splines, which are really parametric, but they're really still implicit. The advantages of these are that they're easy to enumerate and you can change geometry directly. With the implicit form, you have, in 3D, you have a scalar field, just like we saw in the volume rendering lectures. The advantages here are that there is better understanding of global topology of the scalar field, and you have easy in-app tests, so you know if you're inside or outside just by looking at the value of the scalar field. So implicit and explicit, these show up in graphics all the time. They're not unique to visualization, but most of the time when we deal with volume visualization or isosurfaces, we're dealing with implicits. But not yet. Before I go into implicit surfaces, I'll talk a little bit about the most common form of explicit surfaces you'll probably see in scientific visualization. And these are height fields. So height fields are really just a 2D image where the height is the value of the field. So you have some f of xy equals h. And usually this is stored as a simple 2D raster image. Not always. Very often it comes from a point cloud from LiDAR, and you end up wanting to regrid that onto a raster image and then reconstruct the mesh in between. There's several different ways of representing a height field, of representing the mesh itself. One is you can have a physical mesh that has all the vertices and all the indices, everything's connected, and that would be sort of the explicit representation. And in another way you could represent it is sort of half implicit, half explicit, would be to have just the raster image and then parametric patches that are defined at each texel of the height field. And this is really more of a parametric representation, but when you're rendering that directly, for example, using a ray tracer, that would be a ray implicit surface intersection. It would be a 6th degree intersection. And that's really an implicit surface you'd be pulling out. So terrain visualization is really a combination of several different data sources. Usually you have points in 3 space from LiDAR or some sort of aerial reconstruction, and you can resample this onto a grid in a variety of ways. And once you do that, you have a digital elevation model, or DEM. And a lot of the time, you have a coarse DEM, and you want to match that up with color information, a color texture. So that's RGB data. And you end up with a function that looks like f of xy equals height, then RGB. And you want to find a nice way of rendering that. Probably the state-of-the-art paper that I know of for doing this is work from Rudiger Westermann's group, specifically Christian Dick, who basically wrote this incredibly efficient out-of-core system for terrain rendering that was able to render something like a 5 terabyte data set off of disk at 135 frames per second and show all of the varia in one place. And the magic tools for the trade for doing this were essentially the same techniques that you use for fast game rendering. The S3TC texture compression in DirectX that I think gave them a factor of 6 compression of the color field data, and they also use an adaptive split quad tree representation to subdivide the mesh and do level of detail. And this is, I think, still pretty much state-of-the-art in terms of what people would use for height field rendering. Again, this is a DEM, a single mesh or data store of all of the varia that they've split up into tiles, and they're able to pull tiles off of disk, out of core. 5 terabytes of data, quarter meter resolution LiDAR. And this is what the mesh would look like underneath the hood using their split quad tree representation. Now, as you can imagine, this is a lot of geometry and a lot of texture data being streamed to the GPU, and you're never going to be able to fit all of it or get all of it as quickly as you'd like if you're moving the camera quickly. Eventually, it will all stream in, and you'll have your whole mesh kind of converge, but you'll sort of wait as tiles fill in, kind of like you do in Google Earth. So when you say 135 frames per second with an out-of-core system, it's not completely without caveats. And to solve this, they not only looked at the explicit approach, but the implicit approach. Instead of streaming geometry directly to the GPU and having a lot of geometry, they looked at a technique for raycasting patches directly and not having to subdivide and stream geometry or as much geometry. And this saved a significant amount of memory when they did this. The raycasting technique was actually quite a bit faster for fine resolution meshes, the quarter-meter resolution, but it turns out that it was also quite a bit slower for coarse resolution meshes, where you don't have to subdivide as much. You wouldn't see it if you look at it, but the Utah data set here is at, I believe, 1 meter resolution, and the Vorarlberg data set here is at quarter meter, and this was, I believe, 2.5 times faster with the raycaster. This was quite a bit slower, almost 2 times slower with the raycaster. So different techniques are good for different data sets, even if they look very similar. It all depends on how much you want to be able to stream, how well an out-of-core solution works, and whether an implicit or explicit representation is the right one. I'll show you some of these projects because I think they're extremely cool. So one of them is from someone who's working at EVL and graduated right about the same time I was coming to Argonne National Lab. And this is a
planetary scale terrain composition algorithm. We overlaid the National Elevation Database, a 17 gigapixel height map covering the United States at 30 meters resolution, with the Shuttle Radar Topography Mission, a 3 gigapixel height map covering the world at 500 meters. The color map is Blue Marble Next Generation, also 3 gigapixels, for a total of 23 gigapixels of source data. This data, and the demonstrated camel pattern, are the same as those used in the performance analysis included in our paper. Let's look at the individual steps performed by the terrain composition algorithm. First, the CPU computes a coarse set of visible triangular patches. These are uploaded to the GPU for recursive refinement, seen here.
So you can see
this
very
mesh is processed by the GPU
paper
as an image, allowing an arbitrary number of height map textures to be composed directly with it. The texture coordinate of each fragment is written to a 32-bit floating point frame buffer. Here we see longitude in red and latitude in green. Given this, an arbitrary number of surface maps may be composed atop our terrain geometry using ordinary alpha blending in screen space. In this case, the many pages of virtual texture are seamlessly blended. Similarly, normal maps derived from our height map textures are accumulated. Finally, the diffuse color and normal map buffers are combined with an atmospheric illumination model, yielding the final image. Now we see the algorithm operating in real time on a large-scale, high-resolution virtual reality display device. A cluster of PCs drives an array of 60 autostereoscopic screens with a total resolution of over 100 million pixels. The scalability of our algorithm makes it uniquely applicable to this type of display environment.
This looks very nice, by the way. If you go to EVL and see their Cave 2 system, which is essentially the successor to what Bob Koima was working on, I highly recommend it if you get the opportunity.
This video demonstrates the planet.
And I think in terms of novelty, in terms of new techniques, there's really not too much there, aside from the fact that they put everything together and they're able to make this work at very large scale on a planetarium. When I see this work, I think it's actually probably one of the best examples of scientific visualization using conventional fixed function graphics pipeline techniques. And how many of you took a look at the 3JS Mars terrain rendering example that I sent? Oh, okay. Yeah, I'll bring this up really quickly. So I think this is kind of interesting. I'm not sure how many more of these we'll actually see in the future, but the fact that a mainstream newspaper like the New York Times is interested in having people recreate something like the Koima paper at home using Google Cardboard, who's heard of Google Cardboard? Yeah. So essentially, this is the poor man's Oculus Rift, but they claim it works extremely well. I haven't tried it out with their 3JS application, but this is really just the exact same technique with a little bit less optimization. Okay, a lot less optimization, written in 3JS in JavaScript and accessible from absolutely anywhere. And it may not be as fast as what you'd get on the latest and greatest hardware in a lovingly hand-coded out-of-core implementation, but I think one could actually do an out-of-core implementation in Three.js with a lot of pain right now. And hopefully that will become less painful in the future. And in principle, there's nothing technically prohibiting us from doing what the terrain rendering masters of 6 or 7 years ago were doing completely in the browser, accessible to anyone. So I'll just launch this up really quickly. So I wish that you actually got to explore all of Mars. That would be pretty impressive, but I think it would take a little while to load. So I mean, this is just a sort of a standard DEM that's been wrangled through the ArcGIS toolset, converted to an NV file, then converted to a mesh that you load into Three.js, and they've texture mapped it, and that's pretty much all we're seeing here. Let's see, they have a little technique that prevents you from zooming into the ground, but no way to crawl across the ground once you've hit it. And if you zoom out, you'll see the whole crater area. But this will kind of give you a sense of what you can do in JavaScript right now. Okay. So moving on. So I just talked about height fields and terrain rendering, and now I'll talk about contours. So Alex, did you go over contours before? And no. Oh, okay, good. I wanted to make sure I wasn't duplicating too much material. So in 2D, a contour at an iso value v of the scalar field f of xy is the set of curves where f of xy equals v. So it's curves where the value is the same, basically. And when the main field where you would use this is cartography and topography, especially topography, where you're really interested in looking at height. And the main design choices you have there are to look at it as a plan, which is sort of the conventional way, or also you can look at it as a profile, which is just looking at the height and fixing one of the axes. There are many ways of representing the contour. You can use line width dashes, dots. You can label them with the ISO value, as you see here. It's fairly intuitive. In terms of design choices, Mariah very kindly advised us to use different colors at a bare minimum for multiple contours. And she's asking us, why is it best to use multiple contours and to be able to represent them differently? Anybody? This is actually a kind of a rhetorical question. It's because if you don't do it, you end up with a big mess, and you're not really able to tell which way is up and which way is down with respect to the scalar field. So look at this image here in the bottom right. Can you tell if this is a hill or a valley? I can't. So very often you'll have plus or minus symbols that do that tell you where the so-called critical points are. I didn't really put too many slides on topology there, but generally in 2D you're looking at minima, maxima, and saddles. So the maxima, so supposing these were maxima, they would be here, then you'd have a saddle here, and then the minimum would be off here someplace. And that's, I guess, one of the big problems with not just high field rendering, but you also see this in volume visualization, where you're not really able to tell intuitively which way is up until you start to play with the contours and start to adjust them yourself. And then it makes sense almost immediately, but until then, not so much. And you can also see why, instead of just color mapping a height field, so the height, mapping height to a color using a standard color map, you can see why contours are more useful than that. You're able to all of a sudden determine that there's this whole mostly flat area of the floor of the valley that has more or less the same height, and then you see contours that actually would be very, very sensitive to value, just because the range is not changing very much in that region. the gradient would end up being very, very low in this region. And when gradients are low, you tend to have ISO values or ISO contours that are going to jump around a lot. But you're still able to pick out a lot of information from the contours that you wouldn't be able to just by looking at the raw data. And what's also interesting about contours is that by specifying a boundary, you're able to say, I'm interested in the area within this contour. And this definitely applies to 3D. So all of a sudden, contours give you this way of quantifying what you're looking at that you didn't really have before. And I say this more than their usefulness as a visual modality is what makes them so enduring both in 2D and in 3D. So how do we actually do an isocontour in 2D? This is going to be the simple version of what we do in 3D. Generally, we're looking at where the ISO values have a sign change, or where you have one value that's lower than the ISO value, and another vertex that's higher than the ISO value. And when those crossings happen, that's where you actually want to place vertices. So if you connect all these vertices together in the form of a polyline, you end up with your contour. Easy peasy. And in 2D, you have, I think it's 15 different cases that you need to look at. There's actually a way of simplifying this down further, but without taking advantage of symmetry, it's 15 cases. And there's just one problem. What happens when you're looking at, when you have sign changes along all four sides of the squares? How do you determine which way a contour is going? And specifically what's happening here is there's a saddle somewhere in this data set, but we don't really know which way to connect it. If you're looking at isocontours that have a saddle here, or if they're going this way, or if they in fact touch exactly. And there's no way of doing this without subdividing the square further and further, and doing contouring at a finer resolution. There is actually a technique that you can use that will solve this problem called the Asymptotic Decider, and this made a huge splash in the 3D contouring community and in that problem. I'll talk about that in just a few slides. But needless to say, we have this problem in 2D as well as in 3D. And in a sense, going back to this ambiguity problem, there's no right solution to this. The only thing that you can do is make a choice and pick a convention and stick with it. And that's exactly what they end up doing in the case of the asymptotic decider in 3D. So now we're going to talk about isosurfaces. So we talked about 2D contours. And an isosurface is really just a contour of a scalar field in 3D, similar to how an isocontour is a contour in 2D. Given an iso value V, the isosurface is the set of points along the surface where f of x, y, z equals V. And if you extract isosurfaces from a volume data set, there are here two examples. This is a large-scale direct isosurface ray casting example from Steve Parker's 1998 paper. And this is an example of the delta wing with marching tetrahedra. And one thing that's interesting here is that you can see there's very, very fine detail close to the tip of the delta wing. And there's so many, many triangles here. And much coarser detail as you get further away. And a lot of that has to do with the quality of the original mesh and the fact that marching tetrahedra and tet meshes are inherently adaptive. But that's something that you see over and over again in isosurfacing techniques, is that you're really limited to the underlying mesh that you're working off of. So more generally, I should throw out this terminology because you'll probably encounter it again if you haven't encountered it already. Very often in the graphics and CGD and computational geometry communities, you'll hear people talk about level sets. And a level set is really just a fancy way of saying isosurface, or things that are beneath it or above it. in range space. So the level set is exactly the isosurface, but generalized to Rn instead of R3. And it's the set of points x such that the implicit function f of x equals c, the iso value. And in R3 it's an isosurface. And the sublevel set, if you go back to that example I had with the sphere, the sublevel set would be the inside of the sphere, where the f of x would be square root of x squared plus y squared. And the superlevel set would be the outside of the sphere. And both superlevel sets and sublevel sets are bounded manifolds in Rn. Bounded in one way, but that really depends on what your domain is. In practice, our volumes are bounded, so all of these end up being bounded manifolds on both sides, because we're not really rendering in all of Rn. So how do we do isosurfacing in 3D? I'm pulling this from Josh Levine's slides, and he has a very practical way of looking at it. It's a bit like volume rendering, in fact. You have a big 3D volume, a big 3D block of numbers, your scalar field, and you want to turn it into a bunch of triangles. And if you take a bunch of slices, that shows you what the data look like, but it doesn't really show you the shape of the surfaces inside. And this is exactly why you would want to isosurface. And this is, if there's one paper on how to isosurface, this is the paper. When Josh developed these slides, I think 2 years ago, there were about 10,800 citations, almost 10,900. And now today, there are an additional 1,000 citations for marching cubes. So in the space of 2 years, we've had an additional 1,000 sites. That's pretty nice, yeah. It's needless to say, the Lawrence and Klein marching cubes paper has been cited a lot and used a lot. At one point, it was proprietary code. It was patented, and I believe owned by either, I think it was either GE or Kitware itself, but I think it was GE. And then Kitware, then the patent.
It finally expired.
It finally expired. Okay, the patent expired, and Kitware probably derives a good portion of its business and whole methodology from this one single algorithm. So the idea of marching cubes is actually very simple. It's very similar to the marching squares example that I gave just a few slides ago. The idea is that instead of looking at a square, you're going to look at a cell where you have 8 vertices of the cell or the voxel. And each vertex is going to be classified as being inside or outside the isosurface, given the iso value. And the idea is that given this inside and outside, classification from each cell, you're going to get a list of edges, and you're going to map that into a lookup table that's going to classify the inside-outside index based on what it looks like. And that will give you the, not the position, but the edges that you want to interpolate, so which ones actually have a crossing. Then you interpolate them, optionally compute gradients and deal with ambiguous cases using the asymptotic decider, and then you go on to the next cell. So you're basically doing this for every cell that has an isosurface in it. And this is what your voxel looks like to begin with. Just the 8 vertices of the cell, 6 faces. So the first thing you do is the inside-outside test. So if you have iso value 9, then 10 is going to be outside of it. And if you have, and you can actually do this for multiple iso values at the same time. This is one thing that's worth noting, is it's possible to extract multiple isosurfaces, multiple meshes at the same time, looking at each cell once. But let's just focus on one isosurface for now. And the idea is that based on one of these, you're going to have, if you have an iso value 9, you're going to have one classification of the vertices. For iso value 7, you'll have a different case. And each of these is going to be, can actually be stored as a single number, an index. So you have if you use a 1 to represent inside and a 0 to represent outside, then a single 8-bit value, a single UChar would be able to represent that, and you're able to build that into a case table and use a lookup table to basically find out which case you're in. And it turns out that, and this was found exhaustively by Lawrence and Klein in their paper, but it turns out that there are, in theory, 256 cases that you can have, but if you reduce this down to the unique cases, then you really only have 15 cases in marching cubes. You have essentially starting with no crossings to 1 vertex crossing, then you have 2, and then you have 3 vertex crossings, and then you have some 4 vertex crossing cases over here, and that's basically all you can have in marching cubes. So any isosurface is, at least isosurface as a piecewise linear polygon, a strip, as we're doing it here, it is going to be one of these combinations in marching cubes. So here we'll go through the case table in a little bit more detail. So the case 0 is essentially no crossings. There are 8 values above the ISO value and 0 below. Case 1, you have 7 ISO values above and 1 below. Cases 2, 3, and 4, 6 above, 2 below. You're kind of starting to see the idea here. And then you have the 5 above, 3 below cases. And actually, these cases start to be the, I'm sorry, it's not these, it's these ones that start to be a little bit trickier because you can start to have that saddle problem, the ambiguity problem. So again, you have the index, which is just an 8-bit value, and you're able to get the edge list, so which edges have vertices at them, and you just want to find out what the vertices are. And using the vertices and knowledge of which case is which, you're able to piece them together into a set of triangles, and we just use linear interpolation along the edge to find that. Just like we used trilinear interpolation to find a sample in volume rendering, here we're doing linear interpolation along a 1D edge to find out where the edge of the polygon would be. What you also can do is you can compute either vertex normals or face normals. Most of the time you would want to do vertex normals just by interpolating the centrally different normals at the vertices of each voxel. This will mean that when you actually rasterize something on the GPU, you can have beautiful looking gradients and Phong lighting instead of something flat and yucky. And that's basically it. Now the fun part, the ambiguous cases. So 3, 6, 7, 10, 12, and 13. So if you go back to this table, it's 3, 6, 7, 10, 12, and 13. These are all the cases where you're not really sure where the surface is going. If it's if the surface is spreading out this way, or if it's spreading up this way, but in 3D. So you have another dimension. You can go out this way. The idea here, the problem here, is that there's a saddle somewhere in the cell that you're looking at, somewhere inside the voxel, and you don't know exactly where it is, and you need to know something sort of globally about the rest of your scalar field to be able to make a decision of where you think the isosurface is going. Sort of if it's a left, up, or out. And in a sense, there's no right way to do this because you have to know if the scalar field is going up and down at the same time. So you have to make a choice of which way is up and which way is down. And Greg Nielsen and Bernd Hallman, then at Arizona State, now Bernd's at UC Davis, they came up with a solution to this, which is actually fairly highly cited in its own right because it solved the major problem in marching cubes. And this paper is called the Asymptotic Decider. And the idea here is that you're going to look at the faces of the cube that you're trying to extract via marching cubes. And you note that the contours, the 2D contours along the faces of that cube are actually hyperbolas. And if you know something about where those hyperbolas fall along the faces, then you actually can decide if you have two hyperbolas that are spreading out this way, or if you have hyperbolas that are spreading out in the other direction. So the idea here is that you are going to take your vertex and you're going to find sort of the center of the hyperbola. And this is the S alpha, T alpha, and you're going to determine if it's separated and in which direction. And you use this using simple linear interpolation steps over here. And in a sense, this looks fairly non-intuitive, but what you're really doing is once you find the center point, you're really subdividing the face into 4 separate areas. And you're using that subdivision to determine which side has the actual contour, so the actual part of the hyperbola. And once you have that, you know which way the hyperbola is spreading. And that will tell you which way your isosurface in 3D is spreading. And you do this for all 6 faces, and you're basically able to tell where the saddle is and where the isosurface in 3D spreads out from the saddle point. So we go back to the cases 3, 6, 12, 10, 7, and 13. And these are cases with at least one ambiguous face. And this is exactly what the asymptotic decider would let you solve. Would be these cases where you don't really know if the isosurface is going out this way or if it's going out this way. So in summary, Marching Cubes took a challenging problem, a 256 case classification, and reduced it to 15 cases by symmetry. In fact, there's a paper that later reduces that to 8. I'll cover that in just a few slides. And the asymptotic decider paper from Nielsen and Hammond solved the problem of which isosurface is going which way in the ambiguous cases. Now, what do you do with the triangle data once you have it? In practice, you end up with anywhere from 0 to 5 triangles per cube. It's minimum 1 triangle per cube, because otherwise you would just discard it. That's the 0 case. And you have to stitch this together into one big mesh. And there are several ways of doing this. I'd say probably the current state of the art, there are 2 papers that I didn't actually mention in my slides here, but if you look at the NVIDIA CUDA SDK example for how to mesh from their Marching Cubes implementation, I'd say that's actually a very good reference for what to do in a data parallel setting. And more recently at IEEE LDAP this year, there was a paper from Will Schroeder and Rob Maynard and Berkoveci called Flying Edges, that is essentially more efficiently streamlining classification of the edges themselves and spitting out a mesh for many edges in parallel as opposed to just doing 1 cube at a time, as Marching Cubes does. And this is a very efficient implementation. I think they got like a speed up of, what was it, something like 3 or 4x over standard Marching Cubes. Anyway, enough about that. These are the sorts of renderings you can get from meshing standard small volume data. Here we have multiple semi-transparent isosurfaces. We have a low ISO, so this is from the neg-hip data set. You have a low ISO value to a high ISO value. More often than not, you'll see that. If the data are monotonically increasing as you go towards the center of the scalar field, you'll end up having the ISO value shrink as you get to the top. It's a little bit like what you have in 2D with a topographical map, where you have low values on the outside, low elevation, and then high elevation in the inside. And this varies from data set to data set, but that's, I'd say, the convention more often than not. Let's see, this is, I don't think this is from the original Lawrence and Klein paper, but this is what happens if you have judicious pick of ISO values for standard medical data sets. You're able to classify the brain, the internal organs, all these things that we can do with 1D transfer functions and volume rendering, but need a lot of work and a lot of effort. And it's lastly worth mentioning sort of the Achilles heel of Marching Cubes, and that's the effect of grid size. if you don't have gridded data to begin with, and you don't have a native resolution for your implicit, then you basically have to pick your resolution, and marching cubes is very sensitive to that resolution. So if you use a very low resolution, you get horrible reconstruction. If you use very high resolution, you get very nice reconstruction of your implicit, but you also have a lot of geometry. And that's, I'd say, what most of the variants of marching cubes since then we're trying to solve. I should mention actually the paper that preceded the Lawrenson and Klein 1987 marching cubes paper, and this is the Wivel, McFeeters, and Wivel Blobbies paper, data structure for soft objects. And that is more or less doing exactly the marching cubes algorithm without the 15 case tables, and it's not quite as well optimized, but it's more or less the same algorithm, but applied to general implicit blobby shapes defined by Gaussians or other radial basis functions. And the question is, why does this paper, which is really about the same technique, why did this have 1,000 sites, even though it came out a year earlier than the marching cubes paper, compared to the marching cubes paper, which has 12,000 sites? I think this really shows that visualization cares a lot about application as well as raw technique. The idea that you'd use blobbies for animation, that's neat, but the idea that you could generally extract isosurfaces from general purpose CT data, that was revolutionary. And one of these papers ended up having 11,000 sites plus, and the other one is still very well cited, but it's always known as the other marching cubes paper, even though it's in fact the first marching cubes paper. Excuse me. It's also worth mentioning marching tetrahedra, which for a long time was the most heavily used surface extraction algorithm because marching cubes was still under patent. It's quite a bit simpler than marching cubes. There are only 8 cases to consider in a tetrahedron. And also, whereas the implicit surfaces for a trilinear interpolant are piecewise, well, I guess they'd be piecewise cubic, they're only piecewise linear in the case of tetrahedra, which makes it very, very nice if you care about having accurate-looking geometry, facets that look natural, accurately representing the isosurface from a first-order finite element simulation, for example. The flip side is that if you're using this for more general isosurfacing, it generates horrible triangles. And a lot of the time in animation, they'll try to fix this with Laplacian smoothing, but this is expensive and you still have horrible triangles even after Laplacian smoothing. So short marching tets is worth knowing, but it's still less common and less used than marching cubes. But going back to marching cubes, in addition to the asymptotic decider, the ambiguity problem, there's this fundamental problem with marching cubes that if your scalar field is sampled at an off angle or undersampled in any way, or if your grid is, the original grid is not really good enough to represent your scalar field, this problem is going to come back again and again in any marching cube isosurface reconstruction you do from that grid. So, especially in CAGD and milling applications, this is something the geometry processing community struggled with for many years, is how do you fix marching cubes to deal with this problem? Adding resolution just doesn't make these problems go away close to the edges. So what this paper from Leif Kobelt in SIGGRAPH 2001 did was essentially to resample the entire scalar field into a separate distance field and place samples aligned to the gradient of that distance field based on where we'd actually like to see, where we think we'd like to see the edges go. And if you do that, you're able to more or less reorient the edges. They call this edge flipping until you end up having a nicely oriented edge. And the rest of the surface is more or less the same marching cubes sampling that you had from before. So if you apply this to CAGD and milling applications, you're able to get something very nice like this. Another paper, I'd say probably better known, is even is dual contouring from Ju et al. And then later Schaefer and Warren, which sort of extended this to real data from marching cubes. And the idea here is that you want to take the dual of a quad tree and actually mesh that directly instead of applying marching cubes on raw voxels. So it's not like you're applying marching cubes on an octree, for example, but you're actually taking the dual of that and then you are interpolating along the edges of this dual graph. And lastly, I'll mention this TBCG paper from Decret et al. Joao Comba and Claudio Silva were also in this paper. And this is a technique they call edge groups, which actually further simplifies the 15 cases of marching cubes into 8 cases that are more or less similar. And they're using this to improve something called masset, which is a little bit like the edge flipping technique from Cobalt et al., but a little bit more sophisticated. And they're using this to guide this masset edge flipping like technique in a way that's going to make even nicer marching cubes like reconstructions. So this is probably the nicest marching cubes implementation that I currently know of if quality of triangles is your goal. And now I'll talk about some mesh extraction techniques that are not really marching cubes. They're similar in that they're extracting a mesh, but that's the only thing they really have in common with marching cubes. The first one I should talk about is a paper from John Schreiner et al. From Viz. 06, which is essentially a method for starting with a seed point, building a front from that, using geometry processing techniques, specifically local feature size from the work of Nino and Menta, to determine where to place the next seed points. And generally, these seed points can be extracted not from your raw scalar field, but from a resampled, usually higher order guidance field that's going to tell you this is how you make a nice sampling of your mesh. And if you look at the quality of triangles you get from this is even nicer than what you'd get from the Cobalt paper or the Edge Groups paper. Lastly, there's Mariah Meyer's PhD thesis, which was almost entirely scientific visualization topic and involved using general dynamic particle systems not to sweep across a surface that you're interested in, but to actually sample the entire implicit field, adapt to that implicit field using curvature-guided metrics, and essentially reconstruct an entire isosurface from those particles. And you could do this by meshing the particles, or you could completely leave the particles intact, leave them as points. Either way. And that was, Mariah had several papers in SMI and 2 papers in IEEE Viz based around this idea, more or less. The downside of these techniques is that they take a very, very long time to run. They're not necessarily the most scalable, but they're very robust and give you very high quality surfaces. So looks like I have 10 minutes left in class, so I think we have time to cover splatting and raycasting. So it is possible to render isosurfaces, so implicit surfaces, without any explicit polygonal geometry at all. And one of the first efficient ways of doing this was the Q-splat system from Rusinkevitz, never pronounce his name, and Levoy. And this paper from SIGGRAPH 2000 was essentially a big, massive, multi-resolution point-based system that started with range scan data, so lots and lots of points, and was trying to average these points. In a sense, this is not really an implicit, it's not really a scalar field anymore because they were starting with points without value. But they still wanted to have a way of interpolating them, really extrapolating them, discarding outliers. And in a sense, the Q-splat bounding sphere hierarchy itself ended up being a resampling, implicit resampling of that original discrete data. So it's odd that I have this in an implicit surfaces technique because I would say in one sense this is the canonical example of explicit geometry. It's just raw points, there's no reconstruction beneath those points, and eventually you're going to end up seeing, raw pixelated, raw pixels. But at the same time, they were able to handle something like 15 million points in 2000, which was really state of the art at the time. And the general idea is still is very practical, and you can do even better things with it now that you have fragment shaders and raycasting techniques to work with. So you can take a similar approach to the raw point-only Q-splatting technique, and you can use this for isosurfaces, to reconstruct isosurfaces in a regular grid. And this is what the paper from Chris Coe did. Basically, this was taking the grid, it was trying to pre-classify points near the isosurface that you're interested in, and project them, I guess, take a sample and iterate it closer to the isosurface you were actually interested in. And if you were far away, then you wouldn't bother with this iteration, and if you were close to the surface, then you would use Newton-Raphson. It was all CPU-based, it was all roughly interactive, there was no view-dependent optimization, but the technique basically worked, and you could get fairly accurate per pixel results. There's an improvement to this from Gardin Livnat here at SKI and Xavier Trikosh now at Purdue. And this essentially took this earlier technique and made a view-dependent hierarchy out of it. So essentially built a tree around it and decided which regions of space to call and which to ignore. And in fact, what made this paper so fast was that in regions far away from the viewer, they would use plain old, they would use very coarse splatting like this. And in regions close to the viewer, they would use something more akin to marching cubes. And then in regions that were very, very close, they would use the marching cubes and splatting idea, so the isosplatting idea, and the Newton-Raphson iteration. So this was sort of like a hybrid between splatting and marching cubes extraction. And they were able to get, I think something like 10 to 20 frames per second on a like a PowerPC Mac laptop for data sets that 1 gigabyte data sets like the visible female, which before then you could only really do with an out of core system or the CPU ray tracer. So speaking of the CPU ray tracer, this is probably the technique that I see being re-implemented and used more and more now in 2015, because it's finally feasible to do both on the GPU and CPU at fairly large scale. And the idea here is that you have your volumetric grid, and you want to directly raycast or ray trace the isosurface inside the grid. And at the time, Steve Parker here at SKI, along with Chuck and Chuck Hansen and Pete Shirley and several other people, we're doing this on a large SGI shared memory. They called it supercomputer, but we would think of it as essentially a large workstation, the forerunner to GPUs that we have today, in a sense. And what he did was a two-level uniform grid on top of the original volume data, and a direct numerical solution to solve the cubic equation that was the ray. It was the equation along the ray of the image of the trilinear patch in 1D along the ray. And that ends up being a cubic polynomial. And all you have to do basically is to find the A, B, C, D coefficients of that polynomial as follows, and then you solve it using, there are several different solvers you can use, but you can actually use a closed form cubic solver from Schwartz. So this was really fast for its time. I mean, he was able to interactively ray trace isosurfaces of the visible female, which you couldn't really do on any system, GPU, CPU, etc. back at the time, just for lack of memory. So this was a very compelling idea. You needed a very nice piece of hardware to do it. This really was, if there's one paper that sort of proved the power of large memory workstations for Viz, this was it. And for a quick shout out to my PhD research, a lot of what I did during my PhD was to find ways to extend that to different types of data and optimize it to take advantage of multi-resolution octree data, higher order implicit surfaces, and tetrahedral data. There also was work to essentially take the same technique and apply global illumination to it for even nicer results with depth cubes. Today, you can do, well, actually, not just today, but as of really 2008, you could do more or less the same thing on a GPU in a GPU raycaster, similar to the volume raycaster that you wrote in WebGL, but quite a bit more optimized. And the trick with the GPU is that you're still really limited by speed across the PCI bus, so it's less about the shader code that you're writing and more about the big backend out-of-core system and how you get from disk to memory. But the Enrico Gobetti paper from 2008 probably pioneered this technique. If you read the survey paper from Joanna Bayer that I gave as assigned reading, they'll give you a big, they'll give a big overview of the current state-of-the-art techniques for both isosurfacing and volume rendering. Lastly, one last paper that I worked on was this peak finding paper, which is really about combining volume rendering and isosurfacing into one framework. And in fact, I should mention the work from Martin Krauss, the scale invariant volume rendering, which really shows that volume rendering can be thought of as really just a set of infinite set of isosurfaces all composited together. And there are multiple ways of numerically integrating the volume rendering integral. The advantage of this is that you're able to volume render an isosurface in one place. You get faster performance, and you're able to get isosurface-like quality of features and do it quite a bit faster than you would if you were just sampling a volume data set naively. So I'm going to wrap this up. It looks like I have 2 minutes left. Back in 2012, if I talked to people in production viz at Argonne and other national labs, people would say no one uses volume rendering, it's too slow and too hard. And today, 3 years later, people say, 4 years later, people say no one uses isosurfacing, it's too ugly and too limiting. So I think in the last several years, we've really seen a sea change, where people who once would exclusively use isosurfacing are starting to use volume rendering more and more for visuals. That said, isosurfacing will always be useful for data analysis. Anytime you want to take an implicit surface and use that for meshing or remeshing in the animation world. So I think marching cubes will be here to stay for a very long time. And that's all for the lecture today. Next up is vector and tensor field viz.